Thank you, Nima. Your second lecture.
Thank you so much. So the title of this lecture is going to be Introduction to Modular Theory. And just a disclaimer, this has nothing to do with modular transformations in 2D CFTs. So this is sometimes something that's called Tomita-Takesaki theory. All right, so
the name comes from modules? Or?
I think so. I think, yeah, I think so. I don't know. You should ask mathematicians about that. Okay, so a review of what we said last time. We talked about the algebra of D by D complex matrices. This is what a physicist calls the algebra of observables of a qubit. And let's call it a name, give it a name 1D. It has trivial center. We said every algebra that has trivial center, we call it a factor. And this D is the dimensionality of the Hilbert space. It's unique. There are no other algebras that have trivial center in D times our algebra of complex in D-dimensional Hilbert space. So it's called 1D. Then we talked about a particle on a quantum particle on a circle. This is like a harmonic oscillator, and this is usually called 1 infinity, but this is basically the algebra of this is the algebra of bounded operators on the Hilbert space. So this is the algebra. This algebra is generated by k star, k prime, and this is generated the same way for values of k and k prime. All right, so these were our two building blocks. These are two main examples that we're going to work with. And then we said to construct new quantum systems, composite things, we have three tools to play with. We have direct sum, we have cross product, and we have tensor product. So direct sum is somewhat trivial. I can just direct sum things, and because it's trivial, I'm just not going to discuss it and focus my discussion on systems with trivial centers, factors. So I'm not going to discuss that.
Yeah, maybe I was with the K labels the momentum on the circle in this example.
Yes. Yes.
So, but then when the circle is infinite and K becomes a continuum, is that an example you're going to?
So that algebra that you obtain will not admit any representation in a separable Hilbert space. So your Hilbert space becomes inseparable, and we just discard it.
Delta function.
Yeah, delta function are normalizable. Yeah. So
those you are not.
I'm not discussing those. There is a way to deal with them, but for simplicity, I want to be forgetting about those.
Quantum field theories, of course, you'll talk in
finite volume or mass gap.
Okay.
Yeah. So for CFTs, CFTs put them on a circle. Yeah. Of course, we can discuss other things, but to keep the discussion more compact, let's stick to the simple case. So direct sum, it's sort of an obvious story. Cross product we discussed before. If you have an algebra and some group that acts on it as a bunch of unitaries, you can extend it by declaring that unitary to being an observable. So this is something we discussed, and we're not going to touch upon this anymore. So tensor product. So this is what we're going to work with. But by the way, these are still leftovers of the last part. We didn't get to modular theory. Okay, so what can I do with tensor products? Tensor product, the idea is that I have one qubit. I tensor it with another qubit. So I have 2 degrees of freedom. These are independent degrees of freedom. So if I take a finite number of degrees of freedom and tensor them, I don't find anything new. If this had trivial center, the result will also have trivial center. It's nothing interesting. It's going to be another 1D for a different D. So to get something non-trivial, I have to look at an infinite set of them. So this is what we're going to talk about. These are all the quantum systems that we care about. You'll see quantum field theory is going to be one of these examples. So the Hilbert space, let's say these are qubits, is going to be, let's say this is the Hilbert space of a qubit, H2. So this Hilbert space is bad because it's infinite dimensional and uncountably infinite. Why? Naively, you would say a basis for this is all sequences of zeros and ones that are infinite length. Such a set is uncountable. The reason you see that is that take the numbers between 0 and 1 and look at the first digit. If it's 1, put the dot here. If it's 0, put the dot here. Then move to the next one. If it's 0 in here, put the dot in the middle. If it's 1, put a dot over here. As you go towards the infinity, this is dense. This is called the contour set. But all that you need to know is that this is not countable. You cannot count this set. So this is bad. All right. So what we want to do is that we want to restrict to a sector. And physically, the idea is like this. You pick a state. This is an infinite quantum system. You pick a state, and you only allow finite amount of excitations in this state. That's sort of, and the things that correspond to, yeah, okay, so that's what I will clarify that. So what do I mean by that? Take a particular state. So now I said what I said here. Take the reduced density, so the states of local qubits are density matrices. Take this density matrix to be this, tensor it with the same thing, tensor it infinite number of times. So this is a particular state. And we discussed that I can talk about density matrices, or I can talk about purifications of them. So this is my whole system A now. I can introduce an auxiliary set of qubits that purify these. So this density matrix is purified here and in this way, in some entangled state. And I have, for each pair, I have one of them. These are entangled pairs. So I'm putting an infinite number of entangled pairs. So let's call this psi, or something I never use again, phi. So I have a sequence of half-infinite qubits as my system, and the rest of the qubits as the environment, if you wish. You can think of your system as being this picture. It's on a line. You draw a line, and you say, this is my system, this is the complement. Keep in mind the analogy between this and quantum field theory, which was this was the region, this was A prime, this was time. Right? This is the picture to have in mind. So the fact that every mode is entangled points to infinite amount of entanglement. That structure is going to be present in quantum field theory as well.
That's a very non-local entanglement.
Correct. Correct. What matters is that the entanglement is a cross.
Right. But in a QFT, it would be local.
Highly non-local. Correct. All right. So now, what is your state? Your state is this thing, tensored infinite number of times. You act, so how do you get excitations out of this? You act with an operator here. This I'm going to declare to be my ground state. This is my vacuum. I picked a vacuum. I act with an operator on site 1. I act with an operator on site 2. I act with finite number of operators on n sites. This Hilbert space is finite dimensional. I want to take a limit of this in a controlled way and get a countably infinite dimension. Dimensional Hilbert space. This is the game we're going to play. So what are we going to do? We say, so what are the expectation values in this state? So let me just use a compact notation. For this whole infinite thing, this is just notation. I'm going to denote this by chi. So expectation values are going to be, things like this. Now let's say I define a sequence of such things. I have to define the limits. This is basically trace of, what do you call it, rho A1, trace of rho A2, all the way to trace of rho AN. I only allow sequences such that when I take a limit of n going to infinity, this thing converges. right? So I want, so roughly speaking, how much energy, so I declared this is my vacuum, how much energy this has, roughly speaking, is how much change it does to this state. I declared this to be my vacuum. This is an rho. Phi is the pure state, that's a purification of this. Correct, correct. Right, so if it converges, I'm going to include it. So, or said differently, in more fancier terminology, but it's helpful to think about it this way, take two of such states. So now I have some chi1 and chi2. These are to be understood as some chi acted upon by finite number of excitations. Then I pull out of a hat some sequence of operators alpha n, which are, it's a sequence that have defined how they grow as n goes to infinity. If the limit of this thing converges and is equal to some operator x tilde, I include this operator. Well, if the limit converges, I introduce an operator called x tilde with these convergent values, and I add it to my algebra. Such a thing is called a von Neumann algebra. It's a very definition of a general quantum system. This language was a little bit fancy, but I want you guys to think about it this way. A von Neumann algebra is a general quantum system. When it's finite dimensional, that's all that there is, you know them all. When it's infinite dimensional, there are these limits that are important. What is the physics of this limit? This limit. My operators are always bounded. And if I tensor them, they still remain bounded.
So let me just understand terminology. The difference I thought between a C star and a von Neumann algebra was that when we included only bounded operators, unbounded operators.
No.
Right? That's wrong.
No. The difference is about the limits.
Don't C star algebras also contain limits of all operators?
Yes, but it's a different limit. This limit, I put in expectation values. This is called a weak limit. C-star algebras are closed under the strong limit. I don't want to introduce strong limit. We can discuss that. But this is physical because matrix elements are the things that we observe in measurements. And I want to say if my observables, two observables, give me the same matrix elements, they're the same observables. So it's physical. It's a sequence. For example, let's say alpha n. Let me give an example. Yes, let's say it's the following thing. It's, let's say, for n of them, n sigma x. So I have a way of talking about what is the operator for n sites, n plus 1, n plus 2 sites, and so on. But physically, what we are saying is that this is, so roughly speaking, this is a choice of a vacuum, and these guys are excitations, and I want to allow a very controlled amount of excitation, not infinite. So this leads to.
If I take an order theory,
Yes.
and if I'm at a point and I feel phi of x.
Yes.
So I mean.
That's why, yeah.
So then how do you?
Very good. I'll give an explicit example of field theory. So, but briefly to say it, you have to smooth it out because that thing is infinite dimensional. You never observe phi of x. You observe phi of x next to smooth functions because your measurements have some sort. Your measurements always have some sort of a smooth precision. Of course, I'm going to exponentiate it. You'll see. So let's say this was a Fermi. Yes.
But if you take n goes to infinity, that goes out of your sequence chi, no? I mean, I'm a little confused.
My sequence chi. Sorry, which sequence chi?
Chi is supposed to be with finitely many excitations.
No. So I defined this with finite number of excitations. So chi was my choice of vacuum.
That's fine.
Right.
Oh,
Oh,
chi.
yeah,
You're
chi.
calling chi that. Okay.
Yes.
And then you're allowing for
Finite number of excitations. And now I have to decide, this is a boring system. If I allow only finite number of excitations, it's a finite dimensional Hilbert
You're
space.
asking what kind of how do you
How to
approach
complete it. Yes.
What are you allowing?
Yes.
As opposed to?
Exactly. So
You're saying you're allowing those excitations where the dot converges, or no? I mean, what is the difference?
So the difference is this.
Yeah, the first is an expectation value in a state. The other is a matrix element.
Right.
But can't you subsume one under the other?
So here maybe, let me try this again. So fix your vacuum, chi. Take a sequence. First, if the sequence diverges, throw it out. We're not going to allow such things. Now, if it converges, right, that's a potentially good thing. Now, if it converges, take that, put it in here. Take a finite number of excitation vector here, a finite number of excitation vector here. Now take a limit. If this is still convergent, pronounce this an operator, a valid operator, and include it in your algebra.
So you're saying the states chi1, chi2 are defined as the ones that you would create by acting upon
yes, finite number of excitation.
By operators that satisfy the first criteria.
Right.
And then once you have that space of chi's, you can talk of the operators x tilde, which act in that space.
There's an order of limits.
Example of a situation where the first line converges and the second line doesn't converge. What's an example of something like this?
Oh, I don't have such an example off the top of my head, but let's discuss later. All right. So I said all this to make the following point. Yes. Sorry, interpolate n. Not here, not in this setup. Maybe we could come up with some sort of fancier setup, but this is a pretty simple setup, right? I find an infinite number of qubits, countably infinite number of qubits. All right, so now I want to make the following statement. What this does for you is that it leads to different inequivalent vacua or super selection sectors, even though I have no charges here. How so? Take the following example. Come here, okay? So, and pick one case where your rho is lambda, 1 minus lambda. Pick a second case where it has lambda prime. So I pick two systems, right? One case is rho this. The other case, rho prime, is lambda prime, 1 minus lambda prime. Of course, on one side, you can go from here to here. But to go from here to here on every single site takes infinite number of excitation. That's not allowed. So once you complete your algebra this way, your full von Neumann algebra has, so if this thing is related to some chi of rho, some vector of this type, that type, and this thing is related to some chi of rho prime, this is 0. This is the very definition of a superselection sector. Physically, what it means, again, keep in mind the example of energy. Vacuum in an infinite system and quantum field theory with finite energy density are in different superselection sectors. You cannot go in between them without infinite amount of excitations. This is a very, very formal way of saying the same thing. Without charges. So this is superselection sector without charges. We discussed charges in the previous example. Yes.
Now I think of E as the operator that flips the first.
Sorry, E?
A, just A, A1, A, etc.
Yes, yes, yes.
The A's.
Yeah. Okay, A.
Think of A's as those operators that flip the spin. So they
They are 2 by 2 matrices, complex matrices.
yeah,
Right?
2 by 2 complex matrices, and they need to they need to flip the first spin. So they take
Sure.
it from 0 0 1 1 to maybe 1 0 0.
Sure.
So now this new state is orthogonal to the original state. So trace
Correct.
of rho A is 0. So this limit on top converges.
Sorry, I'm not sure if I understand it.
Think of A as the operator that flips the spin inside on the left. So you have this pure state phi.
This, is this a steady one, vector one? Okay, so this acts on the vacuum, and it gives you what? It gives you square root of 1, 0 on site 1, right?
I need one more. 0 1 0 plus 0. A needs to be 1 0 plus 0.
Sorry, A needs to be,
1 0 plus 0.
okay. It gives you this. Good, then?
And so trace of rho A, I think is 0 now.
Sure.
So now, so this is a good op. So trace of rho 1 to rho that's convergent.
This is a very good observable, but you didn't give me a sequence.
No, the sequence is
Oh, this on every single side.
So it changes the vacuum in the
Good, very good. But there will be states, there will be such things for which this will not be a good operator. Maybe. Yeah, I think so. I think so.
I don't see if you have a finite number of excitations, it will still. Finite numbers.
Let's discuss this offline because I'm sure about the definition. It's an example issue. Let's discuss this offline. We can discuss it afterwards. Sorry, but yeah. Okay, so I want to get to modular theory. So why is this an interesting algebra? It has funny properties. Remember projection operators? If you take any projection operator, here is infinite dimensional. An instance of a projection operator is this. This is infinite dimensional on site 1. This is infinite dimensional. And if you do this, this is also infinite dimensional. A generic projection is going to be something like this, which is infinite dimensional. And 1 minus it is also infinite dimensional. This thing has no finite dimensional projection. This is the very definition of an algebra of type 3, which is similar to where quantum field theory belongs. All right. There's a little technical caveat. Lambda cannot be half. If lambda is half, it's a different algebra. It's called type 2-1. We don't care about that. All right. So one more thing about this algebra is that it's type 3, and it doesn't have a density matrix. Why is that? Well, I said formally take this guy and tensor it with itself infinite number of times. These numbers are less than 1. If you multiply them infinite number of times, every single eigenvalue becomes 0. There are no density matrices. So you might ask me, oh, but we do calculate density matrices in quantum field theory with a cutoff, and we play with them. What are we calculating? If you look at Cardy's calculation of the spectrum of density matrix of the vacuum in a 2D CFT, there's a cutoff there. They calculate the eigenvalues. As you take the cutoff away, the whole spectrum goes to 0. This is just explicit calculation you can do. So that is the sense in which there is no density matrices. How?
Can you explain this one as to the 0? You mean 0 0? That's on the
first site? Yes, first site. So because projections act on
everything. So
correct. All right. So I don't have. Yeah, so the statement was that this guy doesn't have a density matrix. It's simply the statement that if you take the density matrix and tensor it on each side, the eigenvalues keep multiplying. Eigenvalues are less than 1, so they're all going to go to 0. You're not going to end up with a sensible operator. I will tell you exactly what's going on over there. Yeah, that's true. So yes, correct. What you're calculating is that what I'm saying is that there exists no measure you could calculate that's a function of a single density matrix. The,
Entropy has some meaning also, like you say quantum entropy is meaningless.
not in this case, yes, it's meaningless. In quantum field theory, von Neumann entropy is meaningless. There's no meaning to associate with that. What is meaningful is relative entropy that I'm going to define for you. All right. So one important point here about this algebra, which is I'm going to use to motivate modular theory, is that I said density matrices don't exist. However, as Suvrad just said, there is something. Why don't they exist? Because this limit is bad. This is a bad limit. However, if I look at the, so I had the system and its purification. If I had omega and its purification. If I look at, so this is just a system A and it's A prime. I'm talking about one qubit now. If I take omega and over here omega minus 1, tensor it. First of all, this is a symmetry of the state phi plus rho inverse. So let me do this slowly. So this state is lambda square root lambda 0 0 plus square root 1 minus 1 1 1. What this does, well, actually, is that it's a symmetry of it. These density matrices are sorry. I said way too quickly. Yes, I'm taking the same. Yes, correct. No, this is good. So this is a symmetry of the thing, and it's called modular symmetry. What is this good for? If instead of taking the limit of this guy going to infinity, where all the eigenvalues vanish, if I take the limit of this guy tensored infinite number of times, this is a legitimate operator. The spectrum is.
I mean, I'm not, because you said it acts as identity on the ground state.
No, so this is an operator that's non-trivial on left and right. It compensates on the right for what is lost in the left. However, it has a symmetry, which is the state from which this is constructed. So this is just one of the reasons that the thermal field double is nice. If you wish, this is, in the case of thermal field double, this is the statement that boost on the left, going up on one side and going down on this side, is a symmetry of the thermal field double. It's the exact same statement, but written more generically. This is a nice feature of the thermal field double. So boost on the left minus, sorry, I said boost. Hamiltonian evolution on the left minus Hamiltonian on the right. All right, so this is a nice operator. It acts on the full Hilbert space. That's important. It's also positive. And to define it unambiguously, I need the density matrix to be invertible. Or I need the state to be Rieschlitter. Otherwise, I have ambiguities. Which is fine. I can deal with ambiguities, but I have to use a heavier machinery. Right? It means that every mode has to be entangled, or acting on the right, you can create arbitrary excitation on the left. That's entirely entangled. It's not the eigenvalues that matter, it's whether it's non-zero, whether it's invertible. Yeah. All right. So, good. So this is all I want to say about this example. To get the algebra of quantum field theory, I need a minor modification. But this was an important point because I wanted to motivate the modular operator. So to give you in advance some sort of idea where we're going, this is a very, very formal discussion, extremely formal. It came as a huge surprise to mathematical physicists when they learned in quantum field theory, Poincare invariant quantum field theory, vacuum is always Rieschlitter. And further, so which means that this operator, the analog of this operator is well defined. And furthermore, this operator is nothing but some sort of space-time transformation, which is boost. Now what we're going to see is this operator is naturally related to information theoretic properties. So this makes an interesting connection between information theory and geometric quantities that's specific to QFTs. This operator for finite quantum systems is somewhat silly. Whatever I can do with density matrix, I can do with this operator. What is shocking or surprising is that in quantum field theory, this becomes geometric. That is an important part of the story. Otherwise, we wouldn't be talking about this as a physics talk.
So it's always geometric.
Sorry?
I know what you're saying. I mean, because of the isometry of the ADS space.
No, no, no. This is going to be a quantum field theory statement. Pure quantum field theory, no ADS.
Geometric. So
Geometric, boost. So this operator becomes e to minus pi boost. Yeah, yeah. Sorry? For half space. Yeah, for half space. Yes. Well, in CFT, in quantum field theory, actually, yeah, I think there are many instances where we go away from this limit of half space, and we can still prove this. It's just hard. The set of Rieschlitter states is dense in the Hilbert space. Oh, you mean whether there is a geometric picture? In 2D CFTs, yes. Beyond the vacuum, because you get excitations in the vacuum block from geometric transformations. Because you get excited state, but conformal transformations of the vacuum, that's why. So basically, those are unitaries that act on this operator that was geometric to start with, so you get something geometric. But away from that limit, no. Unless you're in large N theories or something, you don't get anything interesting. Anything clean. I will give you an example where so this is going to be the topic of the next lecture. These things are related to correlation functions of quantum field theory. So they're not going to be geometric in full generality. All right. So now this is to the example that you were asking. The next example is going to be quantum field theory. This is time. This is space. One direction. There are perpendicular directions. This is my Rindler right and left wedge. I'm going to declare this was my region. So let's work with the scalar field. Take a scalar field phi of x. First, let's construct the algebra of the full quantum field theory. Take all functions f of x that are continuous, and they fall off fast enough near infinity, because I don't want to do something crazy at infinity. Let's integrate to smooth this out. He gets an operator phi of f. This operator, as you mentioned, is unbounded, so I can make it bounded by just exponentiating it. Let's say self-adjoint. Now, these f's are supported on some constant time slice. These guys generate the full algebra for me. If it's a free field theory, the multiplication is precisely the simple multiplication that you know from free bosons. This is the Weil algebra. It encodes the absence of interactions. And if the theory is interacting, this multiplication rule exists, is complicated, requires normalization of fields and such. This is not covariant enough. You could make this fully covariant, because I picked a time slice. To make this fully covariant, what you do is the following. You say, I first look at my classical equations of motion, Klein-Gordon equation, and find the space of all solutions. Each solution is going to go sit here, and that gives me one operator. This is the fully covariant way of doing it. So this is just one comment in case you're worried about covariance. So now, what we do, how do we define the region, the algebra of a region A? The wrong thing to do would be to try to solve the Klein-Gordon equation on this region, because that would require a boundary condition. I do not want to do that. What I want to do is to look at the full algebra, find those solutions that are contained on this side, and look at the restriction of them on this side that fall off fast enough here.
This side is for all x positive.
Yes. Yes.
The functions which have support, you're not looking only for solutions which have support on this side.
I'm looking at solutions that near here fall off fast enough. That's what I'm looking for.
Fall off to 0.
Fast enough, yes.
This is hyperbolic operator. Box, what is box?
Oh yeah, this is minus still, yes, sorry.
Hyperbolic operator.
Yes.
Space-time.
Yeah, this is Minkowski space, yes.
I mean,
Sorry, I should have said that.
no. I mean, because finding solutions is a little more tricky than Euclidean.
Oh, absolutely. This is extremely hard. In general, it's extremely hard.
Yeah, especially about this boundary condition. So can you please repeat this? I need.
Yeah, so take free field theory for a scalar field. Then I can solve this equation and I can classify.
I mean, you can solve this equation means that I mean, boundary conditions or not.
So with boundary conditions,
Just in the full space time, I can
in
solve.
full space-time, yes.
That I know.
Very good. So very good. So yeah,
But then you said something after that.
yes. So now you take that and that defines your full algebra.
Yes.
I want to define an algebra of a region. So I pick from those set of solutions those that are supported in A.
Can I ask what? It's not important to be a solution. The functions which have supported the half-life.
No, it has to be a solution. Or but what you need is that, or you talk about a constant time slice.
Yes, we talk about a constant time slice, and let's take the algebra of all functions on the constant time slice and just complete.
Yeah, I want to do the covariant way. Of course, I can do it with constant time slice one. Yeah, okay, sorry. Maybe I didn't make a distinction separate. Clear enough. So if you have a constant time slice, you can do this no problem. That's doable. Well, that's easy to do in free field theory. In full generality, if you're dealing with something complicated, you would like to have a covariant formulation. So here's the covariant formulation. It's very, very formal, but this is the way to go.
The set of all functions is much more than the set of functions that satisfy that equation.
Correct.
Phi of f, where f satisfies that equation, I mean, those operators are fewer.
Yes, but I'm claiming those fewer operators are the things that generate your algebra.
So that integral is over the time slice, right?
This? Yes, I'm sorry. Sorry.
Over the whole region.
Sorry. Let me clarify this. Approach one. Constant time slice. C. So you look at all functions that are in this region, C of A. Right? And here are your operators. Your operators are phi of f is an integral of x in A of phi of x. And you have to include in there also pi of f, or g, another of such functions, x in A, g of x, pi of x, the canonical momentum.
I mean, this f of, if you're just looking at sigma, then you can think of that as just some initial condition for your wave equation.
Correct.
Equation. So,
Yes.
so you can specify f over sigma
Correct.
To be what you want. It has
Correct.
support only on this side and nothing. So that's initial condition. And
Correct.
you can solve for the wave equation.
Very good.
So I can take any f essentially.
Correct.
So where does the wave equation come in?
So
this?
okay, so Do you agree that these solutions are in one-to-one? These initial conditions are in one-to-one correspondence. There's a one-to-one correspondence between these initial conditions and the solutions of the full equations. Very good. So when I'm talking about the covariant version, which is the solutions of the equations, it's an alternative way of describing this. Good? Now, what happens? Why am I doing this? This is true in free field theory. In a genuinely interacting theory, you're going to have a hard time talking about the algebra that's localized on a constant time slice. You always have to fatten up a little bit. This is a classical thing. Yes, of course, you can map these guys to those guys. That's why we prefer the covariant form of it. Sure, that's fine, but I'm going to have CFTs and primary operators. Yes. So these primary operators are going to be the analogs of my phi of x's, and I'm going to solve some sort of functions that satisfy, depending on my spin or my mass, satisfy they're in the right representation. Yeah. I was going to say, I didn't get to say that, yes. So, if you just take the polynomial algebra, you have less structure because your operators are not bounded. You have to be careful with domains. You could do that. It's hard. If you want to use modular theory, you can't do modular theory with it. Modular theory crucially relies on the fact that your algebra of operators is bounded. Okay? So you could try to generalize modular theory to the case of the algebra of polynomial operators. People have tried to do this without much success. Or you could try to go down this route. All right. Oh, you do get the Fock space. Those are not in the Fock space. Those are not physical states. Delta, you just said delta function normalizable. Right? If it's a state, a physical state is a vector in the Hilbert space. That thing is not a vector in the Hilbert space. Physical things are wave packets, right? I think that's fair. I think physicists. I don't have to take e to the power of I phi f. I can take any bounded function of the operator. It doesn't really matter. So anything that gets rid of the deep the UV modes. Yeah, sure. Yes.
That's very hard to get when you give bounded functions. Many particle states.
No, sorry. Why? So that if you want one particle states, you fix your mass and the represent. Sorry. Yeah, you fix your mass and representation. You solve that function f.
But you have to put it down inside a bounded function. So if you just had to do phi of f on the vacuum, that's good. But now you have to put it inside an exponential.
Yeah, but that's a coherent state of these guys.
I know. So
yeah.
You will only get coherent states, whereas if you wanted to get a one particle state, that's hard to get via the bounded function.
Sure.
So you only get coherent.
Sure, it's because it's not normalizable.
No, this one particle state could be normalizable. I could smear it to the wave packets.
Yeah, but once you smear it with the wave packet, I can get it too. Yeah. If you smear it with the wave packet, I can get to.
Let's see to phi of f active on the vacuum.
Yes.
Phi of f is also an unbounded operator.
Yes, but.
So phi of f creates a normalizable state.
Correct.
Now I want to get it acting only with bounded operators.
Yes.
How do I get phi of f acting on the vacuum acting only bounded?
There is a way to get the Richelieu theorem guarantees you that you could get that.
Okay, that also I agree with, but I just
yes.
understand how in any is there some more.
Yes, here. Are you happy with approximate?
Yes.
Small lambda. Right? You said wave packets are fine, right? This is what it is. It's really no different. I mean, that's why Richelieu says it's dense. That's why it says dense. If lambda is so tiny, It's just, in practice, you have a one particle state. This is how in the lab people prepare wave functions, 1 photons. They have a coherent state with very, very small epsilon. All right.
But I didn't understand, sorry, why phi of f is unbounded?
Phi of f is unbounded because it has.
No, if f is
Space-time control.
You can do whatever you like with f.
And because the field can be large.
Yeah, f can have arbitrary frequencies, yes.
So you have to put it inside exponentials.
Yeah. So now we get to modular theory. Sorry for rushing it up because I wanted to get to this point. All right. What is modular theory? It's the core of this whole thing was a build-up towards modular theory. So it's an algebraic set of tools and techniques to study a general quantum system. So we define what a general quantum system is very abstractly. There was a lot of math discussions, and we could go in depth in those, but in those kind of discussions. But I want to tell you that now we define that thing, we want to see what we can do with it. There was very little structure in there, right? It was just an algebra with a dagger, and it had bounded operators. There was really not much. Turns out that you could do something with this. It's almost the only thing you could do because these systems include anything from qubits to quantum field theory. So all the equations we write down will hold for all of such systems once and forever. And the natural things that come out are information theoretic. So this was a surprise. I don't know, maybe some people had the intuition for it, but. So what can you do? Take the vacuum of your quantum system. Take operators in the local algebra, on the algebra. What do you have in here? Not much. You only know there is a dagger operation and the state. So define an operator, antilinear, that acts on this and gives you this. So this operator depends on the choice of a state and on the region. So this is an equation. Why does this define an operator? It doesn't unless this is dense. No, it's the same. So for any A, it should satisfy this equation.
So S is the operator which essentially takes.
Yes. So I define an operator by its action on all vectors. Oh, I'm sorry. Yeah. Yeah, sorry. Yeah, sorry. Yeah, so I define this operator by its action on every single vector. Now, this is every single vector if the state is Riech-Leiter. Otherwise, there will be ambiguities. So of course, I close the operator. Let's not worry about that. And now, there's a norm. So this is an antilinear. In fact, there will be an anti-unitary part to it, if this is Riech-Leiter, and then there will be a norm. I want to separate the two. So this is the norm. It's called modular operator. Not surprisingly, it's going to be that modular operator. Yeah, for sure.
So you said Riech-Leiter. What is the mathematical definition?
Oh, Riech-Leiter means that these guys are dense in the Hilbert space.
Dense in the Hilbert space.
Yes. Sorry?
You also want it to be separated.
Riech-Leiter is the cyclic and separating.
Then there's some notion of complementary action.
This equation is well defined if this is dense in the Hilbert space.
Yes.
And that's guaranteed by Riech-Leiter. Sorry, I didn't quite get what you said.
You also want A omega not to be zero for this. Yes, I agree. This gives you a good definition of S. You also want A omega not to be zero for any E. You also want it to be separated. If you just
State omega. The state omega you don't want it to be.
you don't want it to be annihilated by this.
That's right.
You want it to be cyclic and separated.
Correct.
But the vacuum is annihilated.
No, not by
The vacuum,
Not by,
the vacuum is cyclic and separating. Yeah.
because the A doesn't belong to the end.
No, so because alpha is only at the path of the state, so it's not like a
Yeah.
So just confirm, is omega belongs to algebra?
Sorry?
S also belongs to algebra?
No, no, it does not. It does not. It's actually, in fact, unbounded. Okay, I'll say in a second. So here are a few points about, oh, I'm sorry, I forgot to mention this. So I split the operator S omega. I do a polar decomposition. This is the phase part of it, the anti-unitary part of it. Anti-unitary if it's cyclic and separating, or in general, just antilinear. And then this is square half. Now, what are the properties of these operators? First of all, this is a symmetry. You can easily see. Well, actually, not easily, but you can show it. So is this thing. This is called modular conjugation symmetry. This is modular symmetry. The fact that this is a positive operator tells you can associate a Hamiltonian to it, and you can associate a one-parameter unitary flow, which is this thing is called modular flow.
Why do you say one parameter?
T.
T. Oh, delta to the power.
IT, yes. So these are all unitaries.
So you can write it as e to the power of Hamiltonian.
Yeah, well,
Because you said it's a positive operator.
yeah.
E to the
Yeah. Yes. Yeah. So here are three most important results of modular theory that I'm gonna tell you without proving. But this is gonna be very, very important. And if the whole program is to use these three results in one way or another to learn about quantum field theories. So the next lecture is going to be about examples where I use these things to constrain quantum field theories. What are these three things? Fact one, which these are, I guess, it's called a theory in mathematics because they could prove these things. If you start with an operator in the algebra, this unitary flow preserves the algebra. It's important to know that this guy is not in the algebra. Otherwise, it would be a triviality. It's actually unbounded. This operator is unbounded. Because
I'm a little confused by that because ideally I would have thought you wrote delta A omega is omega. Delta A acting on any A times omega, isn't it also A times omega or not?
no, it's not, right?
Because doesn't the S dagger acting on A dagger give you again A acting on omega? So S acting on A omega will give you A dagger omega. S dagger
S dagger is S prime.
give you A omega.
No.
So the equivalence of delta between E and P are P. So actually one way to understand it is you take delta, E omega, you sandwich it with omega B.
Little-
And that will give you instead of B and make it P. That those are the equivalents.
But maybe it helps to say that in this setup, if this is cyclic and separating, you can prove that S dagger is the same thing, S dagger of A is the same thing as the S of A prime. Once you act with the first S, you're still in the algebra. So acting with S prime is going to be tricky. Yeah. Oh, sorry. So cyclic means Rieschlitter, acting with this guy. It takes you everywhere. Cyclic and separating, it means Rieschlitter with respect to both sides. Not only A acting on this guy is dense, but also the complementary region. Vacuum of quantum field theory has this property. Yes, it's not given. It's not true for all states. However, I do have states that are like this. These states are cyclic and separating.
So you're working with a purified system
All the time. In quantum field theory, there's, yeah, I can't write anything that's not purified. Yeah, sorry. All right, so this is the first result. The second result is that this J is antilinear, and it takes operators in A and sends them to the other region. This is an A prime. Yeah, for all A and A of A. I'll give examples. Third and the most important result, the most non-trivial result in my opinion, is that if you take a region A inside B, the modular operator as an operator satisfies this inequality as an operator, meaning that you can stick this inside any expectation value and it will be correct. This is a large number of inequalities. There's a freedom in the choice of a state. There's a freedom in the choice of two arbitrary regions. This is the thing that most important thing that comes out of this formal discussion. This has to be true for any quantum system. It doesn't even matter whether it's reach leader. But I'll have to, when it's not reach leader, I have to tell you how I define this guy. I haven't told you that because it requires a little bit more being careful about domain and range.
But when you define your SA, that was with respect to a given omega.
Yes.
So it's the same, whatever that omega is.
Yes.
Omega is any least leader state, basically.
Yeah.
Not necessarily the vacuum.
No, not, there's a, yeah.
Entangled state.
There are all sorts of excited states of this type. Yeah. There's a dense set of them, in fact.
Okay, so I see. So this is greater than meaning. So you said delta A. Once again, can you say delta A is not in the algebra, but it is. So it's not bounded.
Yeah.
But it is positive. That's all.
It's positive, it's bounded, and
But you said
it's not bounded. Sorry, I misspoke. Unbounded. Positive and unbounded. Yes.
positive and unbounded.
Correct. Sorry, I misspoke. Yes.
Just to say one thing, just very you take a row, the density matrix doesn't exist, but that would have existed in the algebra.
It could have been each of the K.
Yeah, so the row is the part in the algebra. The delta is row times row inverse and the other side.
Yeah. So this can be arbitrarily large.
So it's outside the algebra, that's fine. It's density matrix on A and the non-density matrix on B, right?
Yeah. So let's work out two examples. That's delta. Yeah, that's called modular operator. So I'm going to do that actually right now. I'm going to work out two examples to try to give some intuition. Yes. 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 Regions of space, or
You have two boxes, A and A prime.
correct. So
So it's in one of them. This one.
yes. So region A is inside region B.
Presumably you.
Omega is over everything.
Yes. Yeah, omega is across everything.
But no, I mean, presumably the statement is true not only for a local. There's a general version, presumably for the algebra
Correct.
contained in the
Correct.
algebra.
I'm going to use this form of it, so that's why. Yeah. But yeah, the general
Quantum system is the
algebra.
Is contained is a subalgebra.
Correct.
Of the,
Correct. All right, so now let's try to work this out in the case of qubits, 2 qubits. Take, actually, qdit. So example 1 is qdit, modular theory for qdit. Take your state to be the following reach leader state. So this is k of A prime, and all pk's are positive. Cyclic and separating. Yeah, sure.
So in this discussion, you are talking about, in some sense, mere local operators actually.
Uh-huh.
If I have a Wilson line, of course, all this goes back to
No, so
I have a highly non-local operator communicating.
as long as it's highly non-local, as long as it's contained with this region,
Yes,
it's still true.
still true.
Correct. It's true for, I mean, it's proved at such a high level abstract mathematical thing that there won't be any counterexamples. So for instance, you would say, no, let me say the following thing. So you would say, oh, the picture I drew Wilson loops are going to shrink, right? So you would say that, oh, I'm not going to get anything non-trivial. Actually, that's not true because I said A is inside B. You can take A that has disconnected pieces. You can take A to be the whole space with two holes removed. Now you definitely have non-trivial Wilson loops. And this will apply. These are the places where we actually get something new.
I actually had in mind an open Wilson line. I think I understand.
Yeah, it applies in full generality. But the setups you're thinking about are where we're going to actually look at this to get something non-trivial. All right. So the equation to solve is this. We want to solve S omega acts on KK prime, tensor identity on vacuum, and gives K prime, K, tensor identity on vacuum. This is system A, this is system A prime. Right? I took the dagger. You just solve this. As you plug this in here, you solve it, simple algebra, you find that, let me write down the delta A omega and J omega to just save time. You just solve it, and you find that this is pk over pk prime, kk prime, k prime, k prime. This means tensor product. It's the same notation, compact. Which is rho tensor rho minus 1 if rho is the reductance matrix of this guy. J omega is an antilinear, so it acts in the following way. It acts on some constant complex number on kk prime and sends it to complex number conjugate k prime k. In the basis of omega, density matrix, it's a swap operator, and is antilinear. Just, you solve this. It's a simple algebra. So these are the things that we're working with, and that is not surprising that, I mean, based on the language I used, this is the modular operator that I'd introduced before. Now, it has some nice properties. I have to look at this equation. If I look at this equation and write it down, well, first of all, modular flow is going to be this. I want to sandwich this in this way. So this is delta minus IT. This is delta IT. Or actually, maybe I should say that. You can observe immediately that delta is supported everywhere, in A and A prime. You can see that it's positive because, well, delta you can see is positive because these guys are positive. You can see it's unbounded because this has an inverse power. So if you do this, you're going to see that it only acts this way. These two guys cancel, which means that the result is still in the algebra. It's still confined to the right. So it's a one parameter family of, it's a flow on the right side. Or sorry, left or right, whatever is your algebra.
That's why you need an IT rather than just T, so that otherwise it would be unbounded.
No, if it's,
it would take A out of the space or something.
in principle, but it won't be a unitary either.
It won't be unitary, but
Right.
yeah, but supposing you are not.
We do study those things, actually. We do study delta to different powers that are real. The domain of analyticity of this guy is a strip. So complex strip. Yeah, go ahead.
Simpler question. This delta operator actually is domain of the system.
It's not.
But it can be, right?
I can tell you what it is. I can tell you what it is related to. So No, but let's see what it is.
For CFDs, it happens, you can make this.
Sorry, I can say exactly how it is. I'm talking about states. There was no density matrix, Hamiltonian to be found. If you take a density matrix, every density matrix could be thought of as a thermal state for Hamiltonian. It's that evolution for this Hamiltonian.
That can be the Hamiltonian of the system also.
Then in which case you're doing thermal physics. In which case this becomes a thermal field double, right? And then indeed modular flow becomes Hamiltonian of right minus Hamiltonian of left. Perfect. Exactly. And that holds for any quantum system, CFT, QFT, qubits, that's just true.
But for this Ringler, this thing where it becomes this boost.
That's my next example.
So there it will be genuine
Correct.
dilatation operator.
Correct.
It's not Hamiltonian, but it's dilatation, which is the dilatation.
But I would
When you conformally map it, it becomes Hamiltonian.
I would make the following statement, which is, okay, so, yeah. Take quantum field theory again. Again, the same setup, x and xi's. This is the algebra of right and left. What I'm after is S of omega that acts on phi of, let's just talk about how it acts on a single field operator. The rest of the stuff go for right. Sorry? Delta is a local thing. It's not. This is not a local operator. This is not a local operator. Oh, it's because of this. So you think of density matrix as e to minus beta h, right? In which case this becomes e to, so then this Hamiltonian is, yeah, log delta. Minus over 1 over beta log delta. This is Hamiltonian of A minus Hamiltonian of A prime. Yeah. But this is a game I can play everywhere.
Restricted to A, it's not local.
Restricted to A, what do you mean? Yeah, yeah. So maybe what you're asking. No, but maybe what you're asking is that the action of this guy on a local operator could be understood as a local Hamiltonian of only one side. But the action of this guy on an arbitrary operator that has support both sides is non-trivial. It's Hamiltonian left. So here's the question is about what do you mean by local and versus non-local, right? No, delta never belongs to the algebra in the A. It's rho tends to rho minus 1. It's not in the algebra. Algebra is only on the left. Right?
If you're working with fields or something, can you write down a local thing for delta?
No, it never is.
Okay.
It never is part of the algebra. It never is a part of the algebra. So what we want is that it acts on this operator and sends it to dagger of it at the same point for all these operators that are supported in A. Yes, yes. Vacuum of quantum field theory Poincare invariant. So here's the answer. I'm just going to write the answer. This is CRT multiplied by e to minus pi kx over 2. So let's see this. Why does this operator do this? So first, so this is a boost that does this, right? It's a boost. e2 minus pi kx over 2 is boost by I pi. It's an imaginary thing that I have to do via analytic continuation, acting on phi of t, x, and xi on the vacuum. So this is unbounded, first of all. This is the modular operator to the power of half. It's unbounded. So I can't sandwich the field on both sides by this. I can only say how it acts on this, on the vacuum. This is going to be phi of minus t minus x, xi, this. Then if you apply CRT on top of that, on this state, you're going to get dagger t x x I. So time reversal, reflection around this x direction, and charge conjugation. And 4 dimensions, this is the same thing as CPT. Because there are odd and even dimensions that are different, in full generality and arbitrary dimension, this is CRT. So this is J omega, which is a space-time transformation. And what it does is that if it takes a field like this, Txx, and sends it to minus t minus x xi, right? So it takes an operator here, maps it over here. That's indeed consistent with this equation. This is just boost. Boost indeed preserves the algebra of one side. So now this was kind of a surprise because this formal language led to identifying this operator as something that does have to do with space-time transformations. It's just boost. All right, in the remaining 5 minutes, yes.
Can you show this is unique, this construction?
So this construction is unique if your state is cyclic and separating, Richelieu with respect to the left and Richelieu with respect to right, because that equation defined it. If my state is not like that, then it won't be unique. But there's a canonical way to fix that, and we can talk about how to go about doing it. This is exactly where the ambiguity is.
This first line is like sort of all known.
Yeah.
I think what you're saying is that that operator is being identified with this.
Yes. So this very formal thing that I defined could be. Oh, we will see. I can say it. This gives you new constraints. But actually, let me say it right now, one constraint that you already do recognize, now that you mentioned, I think it's a good place to say it. Take the region A to be this. So take the region B to be this. Take the region A to be this, shifted by some amount like this. Now, if this is positive, the reason is this. So you take the log and a minus sign. That minus sign flips the two sides. You end up with this. Now, they're both half spaces. This is boost for where the center is here. So it's k of x around this. This is k of this guy is k of x, sorry, this guy is k of x around this point, this guy is k of x around this point. Boost operator, if I write it on a null sheet, it's just tu duu minus infinity to infinity u, right? Right? So if I subtract, oh, sorry, xi, perpendicular directions. If I subtract the two, So right side minus the left side, I find 2 pi, p minus. So this tells you, in this trivial case, that null Hamiltonian is positive, consistent with something we do know. But this was a very trivial case. The next order in complexity, the next.
So that's 1 million. One is like integral du on.
So du is this is k of b. K of a is this. Call this some alpha. So remember, it's always the modular operator is always supported everywhere. Boost is supported everywhere. That operator is supported everywhere. And that's this alpha is about which is inside which, right? So you get dxi, integral of du minus infinity to infinity, tu u prime, which is p minus. Now, you might have heard of average null energy condition, quantum average null energy condition. What it is exactly the same setup where B is like A, so there's a perpendicular direction. Instead of shifting everything by alpha, you take 1 point and shift by alpha. So you just move by 1 point. Turns out you repeat the calculation, it's a lot more involved. What you find is the difference is going to be this. So now this is a line operator from minus infinity to infinity. And it has to be positive. This is a new positive operator in quantum field theory we did not know about. So all this math pays off. Sorry?
For each xi, right? This will be du prime for a given xi and
xi.
The transverse direction. Transverse directions, yeah.
There's no xi. There's no transverse direction here. This operator is a line operator, so I can shift it, of course. For any xi, yes. I understood what you meant. Yes, correct. Yes, sorry.
So it's the positivity of this operator.
Right. This is where all this math pays off gradually.
So discovered by this mathematical formulation, or
Yes.
people already knew, and this is
No, nobody knew this. The first proof of this is this calculation in Euclidean signature. Path integrals and all that was the first discovery. Then in 2 dimensions, in CFTs, using all sorts of fancy language of null OPs and all that, people proved this in CFTs. But we still don't have a proof of this in quantum field theory without this. They argued that if you have a... Sorry? Free fields, sure. Yeah, free fields, this was known, actually. For free fields, this was known as a positive operator for a very long time. But this result is any quantum field theory, not even CFT. Maybe. Maybe it was expected.
So for any quantum field theory, it is shown that the vacuum is Frisch leader?
Yeah, for half spaces.
Wow.
Yes. All right. So, all right. I'm just going to say a few more things. So, if I have 2-3 minutes, I'll finish this.
Yeah, maybe we can talk about it. Because I was wondering whether it's for mixed theories or...
Anything, yeah. Anything that...
maybe at some point you have to tell us about this B-Schrader theorem, which is slipping in all over the place.
Sure.
Maybe tomorrow.
I'm happy to tell you.
You can keep on proving under what conditions? Under what conditions?
Yeah, the conditions and was Poincare invariance and Poincare invariance and basically causality. Causality. But,
I guess that's what he means by causality.
yeah. Yeah.
I'm worried about whether, I mean, like gauge theory, where, you know.
Inherently local Wiggins, non-local Wiggins.
Extreme relation of the full Hilbert space. So that if you have that,
Yeah, there any
Sorry.
energy is always larger than motion.
Oh, I see.
But
If it becomes
yeah,
extreme relation, then
so but the problem in gauge theory is, I mean, which not maybe true, maybe. I mean, the fact that there's a physical Hilbert space, which is the BRST cohomology, is embedded in a bigger Hilbert space, which is the one which doesn't have all these positivity properties, doesn't have any good properties, but isn't non-unitary. But you always make statements about the physical subspace of that Hilbert space. Whereas I think it's the full Hilbert space which has all the quantum field theory properties.
I think his algebra will only have gauge invariant operators. Only
yeah. So in the case of gauge theory, or in the presence of symmetries,
Non-local.
locality. I think if Richter fails, the continuation from a Euclidean to a Lorentzian path integral will fail. Path integral and get correlated. That uses exactly the same thing, the analyticity of correlators in the forward imaginary line. That cannot continue from Euclidean to Lorentzian. The extent that we define QFT by Euclidean path integral analytic integration, Richter is the same.
yeah, I think the proof of there is a proof of Richter that uses analytic continuation, which is basically Weidmann axioms. It uses Weidmann axioms, but you could formally prove it using in real time.
Yeah, in real time, but in real time, just by using the fact that the correlators are analogic in some, when you continue forward line.
I think it comes out of modular theory, actually. Analyticity of the domain of analyticity comes out of modular theory.
It's very tricky.
Yeah.
Gravity, what you
Yeah.
just said.
Oh, yeah, sure.
I didn't
Analyticity business.
He's not using any
No,
method
no.
of that.
Yeah.
Oh, gravity is not.
This is flat space quantum field theory.
Yeah, so gravity is yet another can of worms.
But there is no least leader
Gauge
in all.
theory
This is what is worrying me. Now you proved fantastic things in over 20 years. They are applicable to systems you're not interested in.
But
No,
And I'm just saying, what about gravity? You said it's not applicable, right?
all quantum field theories.
No.
That's a lot of quantum systems.
I know that analytic continuation from Euclidean to real time is a big problem on quantum gravity.
I agree. So
but let me just say one.
Gauge theory is even, that's why I want to understand, because gauge theory is more subtle and it's halfway into gravity. Or a quarter of the way.
Holography says it's the same.
Exactly.
I think the problem is not necessarily gauge theory per se, it's about massless particles.
Yes.
Massless particles mess up the analysis quite a lot, but if you have gauge symmetries, you have gauge groups, non-local operators and all that, as long as you don't have like QED massless photons, you're fine.
There's a problem.
QED has a problem. True.
Right, but okay, massless particles,
Certain things, carrot space QFT is a whole different topic. Certain things go through.
I think you should finish now.
Yeah, no, I think maybe I could just, given the time, I should probably just stop now.
Thank you.
okay.
Sure.